Okay, let's get started, please. So, can somebody tell me what we are up to? What are we doing?
Ordered sets.
Ordered sets, right? Sure. So we just got the definition of an ordered set. What was the definition? That you have a set and you have this relation, right? And as long as the relation does a couple of things, then you say that it's an order, right? And the set is called an ordered set. What are the couple of things, just to remind ourselves?
The following is true, x equals to y, y equals to x, x equals to y, then transitivity.
Then transitivity. Yeah, thank you. Okay. So right. So remember, there were two things that had to happen. One is that only one statement could be true between x and y. Either x is less than y or y is less than x, or they're equal to each other. Right? Only one of those things could be true at a time. And then the second was that you had to have a transitive relationship, right? That if A is less than or equal to B and B is less than or equal to C, then A is less than B, B is less than C, then A would be less than C. Okay. Somebody asked me what a binary relation was. And that you can think of as just a relation between two objects, right? So that is either true or false. Okay, for example, the word like is a binary relation, right? Like A likes B. That's either true or false, right? Is that an ordered relation? No, right? Because for it to be true, you have to have A either likes B, or A is equal to B, or B likes A, right? Only one of those could be true at a time, but in reality, more than one might be true, right? You might like somebody else, and you still might like yourself, right? Right? It might be okay. You might like yourself, right? Or transitivity, right? It'd have to be that if A likes B and B likes C, then A likes C also, right? And that's not true. Yes.
And it doesn't have to be a binary operation. We can say we like you.
Oh yeah.
We like everyone.
Yeah. So like is very much not it's not even a binary relation, but it can be used as a binary relation, right? Between objects, between single objects, right? Okay, so ordered sets, right? We defined the notion of an ordered set, and the reason is that we're trying to talk about, the whole point of the chapter is to explain what's so good about the real numbers, okay? And the real numbers are going to turn out to be something that is, in part, at least an ordered set. Hello? That's all right, Okay. Did anybody get to the end of the chapter and say what the real numbers are? Other than Mr. Al? Okay, so Mr. Al, what's gonna happen with the real numbers?
Well,
what are they gonna be?
The best way I can explain in layman terms is that they can be as close as you want, any two of them. If I break the real number into two sets, one of them is entirely below the lowest number of the next one on top. Now, that's very confusing to me, but I guess you can divide it into two sets. An element X of set A, and the other set B. The lowest term of set B can be the highest of set A, and none of set A can pass it theoretically. Consequently, there is a way of looking at it as if from set A you can get as close as you want to the lowest element of set B, but never can't get there. And there is no holes in between. That's what I got out of it.
Okay. Yeah,
and I'm still the unkindest cut of all, the Dodekind cut. That's the way I think about that.
Okay. Yeah. So it's it'll be. It's a tricky concept to describe. So the whole chapter is in fact set up to describe this quality. Yes.
We understand that it's an ordered field with the least upper bound problem.
Okay. Yeah. So right. So right now we're talking about ordered sets. The next big thing that we're going to talk about is fields. Okay. After that, we're going to talk about ordered fields, which you might think are just fields that are ordered sets, but that's not true. They're actually sort of a special thing inside there. So there's ordered fields. Okay. There's something called an ordered field, which is a little bit better than just a field that is also an ordered set. And so the real numbers are going to be a very special thing. They're going to be a field, an ordered field that contains the rational numbers. Okay. And most importantly of all, satisfies this thing called the least upper bound property. Okay. The least upper bound property, that's going to be the crucial thing that we'll use. Okay. Okay. So, okay. So let's, so we've already introduced ordered sets, right? So you have some, right? You have some set, and you have some order on it. You have some set, you have some order on it. Don't be confused. This is not your old friend. This is the new, some abstract thing, an order. Okay. This is not your old less than sign from numbers. Okay. It's something new. Your old friend is an instance of this. Okay. The less than guy from real numbers, that's an instance of an order. That's one kind of order. But this is not that. Okay. This is a more general thing. Okay. But if you want, you can keep in your mind that as an example, and that's actually a pretty useful thing to keep in mind. Okay. Okay. So we got that. Next, once we have a sense of order, once we have an order on a set, we can talk about boundedness. Okay. Boundedness. Okay. So suppose you have S an ordered set. Okay, so let S say S is an ordered set. Okay. And you have E a subset of S. You have some subset of an ordered set. Okay. Again, if you want to keep in your head, maybe you think of S as the real line, and then E as some subset of the real line. That's helpful. Okay. Okay. But just remember, we're not in the real line. Okay. Yeah. Okay. So here's the definition. If there exists a beta in S such that beta is greater than or equal to x for all x in E. Okay. Either beta is greater than x or it's equal to x for all x in E. Then we call beta an upper bound. An upper bound of E. Okay, and we say E is bounded above. E is bounded above. Okay, so suppose we are in this world, right? Suppose that our world is R with the standard order, right? Somebody give me an example of a set with an upper bound. What's an example of a set with an upper bound? Right. What's your name? Right. Right. Yes.
Negative numbers?
Negative numbers, right? So if we let E be, the negative numbers, right? X such that x is less than 0, right? Then certainly 1 is an upper bound. Or 0 is an upper bound, right? So 0 is an upper bound of E, right? 0 is an upper bound of E, 1 is an upper bound of E. There's infinitely many upper bounds of E. Okay, right? So I hope you get a sense of what an upper bound is, right? It's pretty straightforward. Something that's bigger than everybody in the set. Okay.
Professor?
Yes?
Can a least upper bound be included in the set itself?
We haven't defined what least upper bound is, so let me wait to answer. Ask that question when we define least upper bounds, because we haven't defined it yet. Okay. Well, I guess we're going to define it in 1 second. But yeah, but before we get there, I don't want you to think that we're just in R. So let's make another example of a bound, an ordered set. So let's take C as your set, right? Let C be your set, and let less than be the so-called lexicographical order. Lexicographical order. Okay. So you're in the complex numbers, right? And you say that 1 plus I is less than 2 plus I, say. Okay. What I mean by the lexicographical ordering is that you look at the coefficients, right? So the coefficients here are 1, 1. The coefficients here are 2, 1, right? And then you look at it like an alphabet, right? You got the word 1, 1. You've got the word 2, 1 here, right? It's like this. Here's the word AA. Here's the word BA, right? This one precedes that one in the dictionary, in the lexicography, whatever, in the dictionary, right? Right. So this one is less than that one. Okay, right? If I have 3 plus, if I have 1 minus I, I have 1 plus I and 1 minus I, then which one comes earlier in the dictionary? 1 minus I, right? Because I got 1, 1 here, I've got 1 negative 1 here, right? They've got the same first letter, but this guy's second letter precedes that guy's second letter. Okay, right? Okay, so this is the lexicographical order that one can put on the complex numbers. Okay, and this, if you think about it, this works fine as an order. You can check the relations. It actually works. That actually is an order. Okay, so for example, if I say like I'm in the complex plane and here is my here is my set E. Here's my set E. So I'm in the complex plane. Here's my set E. Right? Okay. What's an upper? Somebody tell me an upper bound for this set. So the set is, say, everything with a negative real value. Right? So A plus BI, where A is less than 0. Oh, you actually, people talk to each other for 1 minute and come up with give me an upper bound for this set.
What's the y-axis?
Yeah, let's do it.
So it's obviously anything positive,
As long as it's not
zero,
As long as it's not negative. As long as the real part is not
Oh, I thought you said you could. I was like, what? It's always Oh, you're not? I went to her house actually. She lives in So I was like, why not? No, I was like, have everybody
I couldn't define like a non-lexicographical, like an actual order of sorts, or like do a norm or something for the complex numbers, right? It didn't need to be lexicographical.
If it's a norm, you can have things that have the same norm, but are different.
Oh, so you can stop.
So you fail the first quality order. Okay. Tell me some upper bounds for this set E.
1.
1. Okay, the number 1. Certainly that works. Anybody else?
2 million.
2 million?
I feel like that's
2 million?
in the midterm. Somebody just tries
Yes.
to figure it
X.
1 plus I.
1 plus I. Okay, sure.
out. 2 million plus.
The y-axis, right? Anybody on the y-axis, right? Anybody on the y-axis certainly has a higher real part, right? Has a higher real component than these guys, right? Anybody on the y-axis will do, right? So this whole thing here. In fact, everything on the other side, the complement of this set is basically all the upper bounds of it. Okay. Okay. Is that clear? Yeah. Okay. Okay. So just to give you an example, that's not something that you've seen before, I hope. Okay. Okie dokie. Okay. So upper bounds, right? Just something that's bigger than everybody in the set. Bigger than or equal to everybody in the set. Okay. Okay. So here is the crucial definition. Okay. So again, say E is a subset of S, which is an ordered set. Okay. So E is a subset of S, an ordered set. S is the ordered set. It has some order, which we're always going to use the less than sign for that. And suppose that gamma. No. Suppose that beta is an upper bound. No. Suppose that given any upper bound, sorry, let me see it this way. Suppose that beta is an upper bound of E, and given any other upper bound of E, upper bound gamma of E, that beta is less than or equal to gamma. Okay. So beta is an upper bound with a special power, right? It is less than or equal to any other upper bound, right? Any other upper bound, beta is going to be less than or equal to it. Then we call beta the least upper bound, of E. The least upper bound of E, also called the supremum of E. So you'll see me either write LUB or sup. Either the least upper bound, it's the same term. I like least upper bound better because when I see the word supremum, I always translate back to least upper bound, right? Because that's what it is, right? It's the least of the upper bounds. Okay. Okay. Okay, so this is kind of an odd thing, right? You've got your sets, right? You've got your upper bounds, right? And now what we're saying is that maybe there's some guy who is an upper bound and it's less than or equal to every other upper bound. Okay? I guess that's not so strange, right? That's not so strange, right? Like, if I gave you a finite set of numbers, 1, 2, 3, 4, 5, right? And I said, what is the least upper bound of this set? What is the least upper bound of this set? Something that is greater than or equal to everybody, and it is smaller than any other upper bound. 5, right? 5 is it, right? B. because 5 is greater than or equal to everybody, and if you go less than 5, you fail, right? Okay, so 5, in this case, if it's a finite set, it's pretty straightforward, right? The biggest thing is going to be your least upper bound, right? So 5 here is the least upper bound of this set. Okay, so that's example 0. Okay. Coming to this example that we put out, right? Here you've got the real numbers and the standard ordering, right? You're looking at the negative numbers, right? What's the least upper bound? Turn to your neighbor and say something. Right?
0.
Not too loud. Right? The answer is 0, right? 0, right? Because right, 0 is an upper bound, and you can't get lower than 0, right? Because if you're lower than 0, you're going to miss part of the set, right? Right? You're not going to be an upper bound anymore if you're lower than 0, right? Here's my set is everybody less than 0 here, right? Right? If I 0 is an upper bound, but nothing smaller than it is going to work, right? Nothing smaller than it is going to work. So this is the least of the upper bounds. Okay. Okay. Now, how about in this example, where my E is the open left half plane of the complex plane? Okay. Think about it for 1 minute. Don't blurt anything out. And I'll go walk around outside.
That's the line. Yeah. But you have to pick a point, right? Because you know how even if they have the same rules, they can have different examples. That can make the different order.
That still have the order.
So 1 plus I.
Oh, yeah, it's small. So it's 1 minus infinity. So 1 times 1 minus I times infinity. It makes 1.
Okay. Tell me about it. Yoke.
Is the y-axis, so any 0 plus pi or just 0?
So it's true, anybody on the y-axis is an upper bound, right? Anybody on the y-axis is an upper bound. This is an upper bound, this is an upper bound, this is an upper bound, this is an upper bound. All these guys are upper bounds, right? Now, is there one upper bound that is smaller than all other upper bounds? No, right? Right? Because no matter who I choose, I could choose somebody slightly lower, right? And that one will be smaller. I found a small, I say, is this the least upper bound? Well, no, this is still an upper bound, and it's lesser. It's less than that guy, right? So there's no least upper bound for this set in this world here. Yes, Mr. Al.
Yeah, because I was going to ask you, what's the difference between 0 plus 1i and 0 plus 2i?
Right, so 0 plus 1i and 0 plus 2i, right? 0 plus 1i, 0 plus 2i, right? Here's the word that corresponds to it, right? This guy precedes this guy in the alphabet,
Okay.
right? So 0 plus 1i is less than 0 plus 2i.
Okay. Yeah.
Okay. Important example. Recall the set A, which was everybody in Q that was bigger than 0 and whose square was less than 2, right? And the set B, who was every rational number greater than 0 whose square was greater than 2. Right? Remember these sets? Okay, right? So here is 0, right? We're looking at the positive rational numbers. We're looking at the positive rational numbers. There is no rational number where p squared equals q, as we showed on the first day. Right? There's a hole where p squared equals 2, right? and B is, I'm sorry, A is everybody to the left, and B is everybody to the right, right? Okay. Now, what do you see about these sets? Everything in B is an upper bound of A, right? Everything in B is an upper bound of A, right? Every element is an upper bound of A. Okay. Is there a least upper bound? Is there a least upper bound? No, right? Why not? Because we showed that if you choose anybody in B, if you choose any point in B, you can find somebody smaller than it, right? There was no least, this is what we proved back then, right? There was no least element of B. If you chose this guy as P, right, then you could choose another guy who was still in B and who was smaller, right? Okay, so, like, or I should rather say B is the set of upper bounds, sorry, I phrased it poorly, upper bounds of A. B is the set of upper bounds of A, but there is no smallest element of B. As we saw before, there is no smallest element of B, right? So there is no supremum of A in Q. Right? There is no supremum of A in Q. Right? A is bounded above, but there's no least upper bound. Adam.
So based on this,
Yeah.
any sequence that's analytically incomplete doesn't have a supremum.
Any sequence that's analytically incomplete? Do you mean a set that's
I
analytically
guess, yeah.
incomplete?
If you converge to a point outside,
I think that's true. Let me make sure it's true. Let me get back to you on that. Okay. I always doubt myself, so I'm sorry. You may ask me, is 1 + 1 = 2, and I'll be like, let me think about it. Because shortly we'll say something like, unless 0 = 1, or something like that. Okay. Anyway, let me. This example leads to an important idea, a crucial idea. Okay, so let S be an ordered set. Let S be an ordered set. If it is true that given any non-empty set E in S with an upper bound, there exists a least upper bound in S, then we say S has the least upper bound property. Okay, yeah.
What is the word if it's?
If it is true that
That is true.
this thing holds, then we say the set has the least upper bound. Okay. This is the important one. I guess I keep on saying that. This is the important one. This is also the important one. Okay. So if your set is an ordered set, and it has the property that whenever you have a set with an upper bound, there exists a least upper bound in the space. Then we say your space has the least upper bound property. Okay. Right? If your space has the least upper bound property, whenever there's an upper bound, there's a least upper bound. Okay. Maybe it's clearer to say it that way. Right? If your space has the least upper bound property, it means that whenever there's an upper bound, there's a least upper bound. Okay. So for some non-examples, right, we just see here that Q doesn't have the least upper bound property. Right? The rationals don't have the least upper bound property because look, this set A has upper bounds, right? If the number 4 is an upper bound, but there's no least upper bound in Q. Right? There's no number in Q that acts as a least upper bound for A. Right? So Q does not have the least upper bound property. Right? Q does not have the least upper bound property. Okay. Another one, right? What other example do we have, Eric? Don't forget it. What other example that we just showed shows that some set with some ordering doesn't have the least upper bound property?
Complex.
The complex numbers, right? We just saw that if we have C with the lexicographical ordering, this set has upper bounds, but there's no least upper bound, right? So C with lexicographical ordering does not have the least upper bound property. Okay. We had one example with R that says maybe R has the least upper bound property. At least for that one example, right? There was a least upper bound, right? That doesn't say that R has the least upper bound property. Just for that one example, it worked out, right? We'd have to show it for every set with an upper bound has a least upper bound. Okay, so, but it's easy to show something's false, right? Right? Just find some counterexample. This doesn't satisfy it. This guy doesn't satisfy it either. Yes, Ryan.
You said that if you have the property and then there are upper bounds, there's a least upper bound. There is a least upper bound.
Yeah.
But if you have the property and there's no, when would you not have an upper bound?
When would you not have an upper bound?
Like, I thought it was part of the. You explicitly said that it has to have an upper bound.
Yeah. So the least upper bound property is like this, right? Whenever a set has an upper bound, it has the least upper bound.
Would you ever have a set that had the property but not the least upper bound? Or would that just not make sense?
It doesn't make sense, actually. Yeah. I mean, you can have sets that don't have upper bounds, right? Like if you're in the complex numbers and you look at the whole plane, say, right? The whole plane doesn't have an upper bound. Right, but that's sort of, it doesn't really fit into this setting actually. Yeah. Yes, I'm sorry, I forgot your name. Edward, yes.
Notation-wise, do you prefer using the LUBE or do you prefer using the SUPE?
You should be free to use either one. You should be free to use either one. Yeah, so Abel has just said very boldly that true mathematicians use supremum. So that's. So I prefer to use LUB. but you should be able to use both of them. Yeah. Ellen.
Wow. Okay. Put my foot in my mouth.
How does that subset of the complex numbers not have a least upper bound? Isn't 0 the least upper bound?
So remember what we observed was that these are the guys with negative real components, right? Okay. So anybody of the form 0 plus bi, 0 plus bi, anything with the form 0 plus bi is going to beat this, is going to be bigger than this, right? Because a is a negative number, right? So 0 plus bi for any b is going to be an upper bound.
Yeah.
Right? So anybody on this imaginary axis is going to work. Okay, but there's no smallest guy there. Right? There's no smallest one of them.
Because it's imaginary?
No, but there's no smallest one because suppose you choose one. Suppose you say, I'm going to choose 0 minus 10i. Okay, you choose one. And I say, oh, that's not the smallest. 0 minus 11i is actually smaller than that.
Oh, I see.
Okay, so no matter what you choose, I can find one that's smaller. So there's no least one. Okay, so least upper bound property, right? Kind of a weird one. Okay, so, right, if, whenever you have an upper bound, you're guaranteed to have a least upper bound. Okay? Okay, and I realize I should have earlier, when I was introducing upper bounds and least upper bounds, I should have introduced the corresponding notions of lower bounds and greatest lower bound. Okay, so let me sort of go backwards a little bit. So remember, we have upper bounds. Upper bound of a set. We also have lower bound. You can guess what that means, right? You know what that means. And we have the least upper bound. We have the least upper bound. There's a similar notion, the greatest lower bound. Greatest lower bound, right? It's a lower bound and it's bigger than or equal to all other lower bounds, right? A lower bound that's greater than or equal to all other lower bounds. Okay. Right? And the abelian terminology would be infimum. Okay. I mean, abelian.
Yes.
I don't mean either of those things. The other terminology is supremum or infimum, of course. Okay. Okay. So we've been talking about the least upper bound property. You might also think, okay, what about the greatest lower bound property, right? Right. Greatest lower bound property. Why don't we talk about the greatest lower bound property, right? That what should be the greatest lower bound property? That whenever you have, right?
The lower bound.
Whenever you have a lower bound,
There exists a
greatest lower bound in the ambient space, right? In the ambient set. Okay, right. So you think, well, you know, shouldn't we talk about that? And what you found out in the reading is that you don't need to talk about that. Whenever you have the least upper bound property, you have the greatest lower bound property. They are equivalent. You could go backwards. You could have a universe where everybody talks about the greatest lower bound properties and ignores this one because they're equivalent. Okay, so I think we should have time to finish this up in 10 minutes. So S, an ordered set. Then S has the least upper bound property. Implies that S has the greatest lower bound property. Okay. Okay. So I tend to put this sort of background fact in brackets. Okay. This is important, but it's not the key part of this. Right? The key part of this is that having the least upper bound property implies that you have the greatest lower bound property. Right? This is necessary, but here's the heart of this is the real point of the proof of the theorem. So just in case you're wondering what these brackets are. Okay, so here's the proof. Okay. So suppose S has the least upper bound property. So, I mean, I don't know if you want to do this, but sometimes it helps to make things clear. When I was first starting to write proofs, I always say, you want to show that given any set with a lower bound, there exists a greatest lower bound. So, you don't need to write that. It's if you know what you're doing, that's fine. But sometimes it helps to make it clear to yourself what exactly you need to show. Right? We need to show that given any set with a lower bound, there is a greatest lower bound. Okay? So you say, okay, let B be a subset of S and be non-empty. Right? It has to be a non-empty set. Let B be a subset of S, B be non-empty, and say B is bounded below. Okay. We want to show that there exists a greatest lower bound of B in S.
Why
Yes,
are we assuming that B is bounded below?
I'm sorry?
Why are we assuming that B is bounded below?
Well, because that's what we need to do to prove the greatest lower bound property. Right? We need to show that whenever you have a set that has a lower bound, whenever you have a set that's bounded below, right? Being bounded below is the same thing as saying right? If there's an upper bound, we call it bounded above. If there's a lower bound, we call it bounded below. These are being bounded below means that there's a lower bound. Okay, so I'm just if you want, you could say suppose that there is a lower bound of B. Okay. It's the same. It's equivalent. Okay. So we want to show that there is a greatest lower bound. Okay. Does anybody remember the strategy? What's the strategy? We have the least upper bound axiom, right? We have the least upper bound property. We want to use it to prove the greatest lower bound property. Anybody? I think many of you have read it already. What's the strategy? We're going to use the least upper bound property. Sorry, there's only 5 minutes left, so I'm gonna not let you think too much about it. But the strategy is to consider the set of lower bounds, the set L of lower bounds of B. Okay. Consider the set of lower bounds of B. Right? We know that B is bounded below. Right? So L is not empty, right? B is bounded below after all. Right? It's not empty, and L is bounded above. L is bounded above. Why is L bounded above? How do you know that L is bounded above? Don't blurt it out. Turn to somebody and talk for half a minute. Why is L bounded above? L is the set of lower bounds of B.
So if it is lower bound, it is equivalent.
Suppose that has half the lower bound and the least upper bound property.
Yeah.
The least upper bound, that means every subset has an upper bound.
Max, what's why? Why?
Any element of B is an upper bound.
Any element of B is an upper bound, right? L is the set of lower bounds of B, right? Anybody in L is a lower bound of B, right? In other words, it's less than or equal to everybody in B, right? In other words, anybody in B is going to be bigger than anybody in L, right? Any fixed guy in B is going to be greater than or equal to anybody in L, right? Because L are the lower bounds, right? Because anybody in B is is greater than or equal to any L in L, right? By construction of L, anybody in L is less than or equal to anybody in B. So the strategy is consider the set of lower bounds of B. It's a non-empty bounded above set. So what are we going to use? The least upper bound property, right? We're going to use the least upper bound property on this set. We've got this set, it's bounded above, and it's non-empty, right? So by the least upper bound property, we know that there exists a greatest lower bound of B in S. Right? There exists a greatest lower bound B in S. A least upper bound. What am I saying? Least upper bound of L in S. Okay. We want to show our goal. Show that the least upper bound of L actually is the greatest lower bound of B. So, so first observation, first observe, right? So we have this guy, right? We have this guy, the least upper bound of L. Okay. So, first observe that given any other lower bound of B, then this least upper bound of L has to be less than or equal to that guy, right? I'm sorry, greater than greater than equal to, sorry, greater than equal to, right? The least upper bound of L will be bigger than or equal to any other lower bound of B, right? Because it's an upper bound of L, right? It's an upper bound of L, right? It's an upper bound of L. L is a set of lower bounds of B. Right, so given any lower bound of B, this guy is bigger than or equal to those guys, right? Right, because it's an upper bound. Okay. So so we know that this number that we got is bigger than or equal to any other lower bound, right? Any other lower bound of B. Okay. So the only thing we need to show is that it itself is a lower bound of B. Right, so now it suffices to show, it suffices to show that this lub L is a lower bound of B. Okay. So, okay. So actually, let me stop here because we're running over time. But I'll I'll finish this up next time. Okay, sorry to stop right in the middle.